Dear professors, dear TAs, and dear group members, I'm so excited to present my project, which I have revised that recently on the concepts of the quantization. The thing which I'm just going to do in this very short presentation is that I'm just going to borrow the concepts from the quantum physics, particularly the Schrödinger equation, apply that to a very well-known and prevalent concepts in both classic and quantum physics, which is going to be the concepts of the oscillation, to introduce the quantization of the energy, and also at the same time we see a huge difference between the classical physics and quantum physics as a result of the quantization, which is the concepts of the zero energy, which is something which we do not see that in the classical physics. And at the end, I'm just going to use these methods of the quantizations to talk about the lasers and ultra-fast lasers, which is going to be one of the brilliant examples of the quantization of the energy, which is available to us based on the concepts of the energy quantization. Okay. In this slide, you are going to see, I should say, on the left, you are seeing essentially a mass, which I say that its mass is going to be the m, and it's at the equilibrium position because you see that it's at the equilibrium position x equal to 0, which no force is acting on it. If you use a force to just push the mass going, I should say, towards, the wall, in the other picture, you are just inferring a kind of, a potential energy and at the same time a kinetic energy of this motion. In the classical energy, you can describe this dynamics based on two different kind of the energy. The first one, if I just show that E as a total energy, it's going to be the sum of the kinetic energy plus the potential energy of this motion. I'm just going to substitute the relevant terms for these two type of the energies. For the kinetic energy, because this mass is moving with the kind of a velocity, I'm just going to show that it's going to be 1 over 2 m v squared plus, and also its potential energy, which is going to be 1 over 2 kx squared. The x is going to be, I should say, essentially the contraction of the spring with the rigidity of the K in that, in that system. However, as what we have seen in the quantum physics, we can describe the same thing, the same total energy in the quantum physics, concepts. But in that sense, we are just going to use essentially the Hamiltonian and the Schrödinger equation, which you have seen that we can just write it as I h bar over partial derivative of, the energy state of, the psi. I use the Dirac notations for that. It's going to be the Hamiltonian of that system, of that dynamics on the kit of that system, which we are going to talk about that. In that sense, now the thing that we are just going to talk about is that now we are just going to say, okay, the same energy in the quantum physics now is going to be written as a Hamiltonian. In the Hamiltonian, what we are just going to do, we just use them as a kind of an operator. I'm going to talk very shortly what do we mean by the operator, but remember that the Hamiltonian historically replaces the concepts of the energy in the classical physics, but it uses, the same concepts. We're going to talk about the kinetic energy. In that sense, 1 over 2 mv squared is going to be replaced by the linear momentum of the mass, which is moving and oscillating, divided by 2m. And by remembering that the p is the mass times the velocity, we can just get the same expression, 1 over 2 mv squared. And also, I'm just going to write, in respect to the kx squared, I'm just going to write that it's going to be 1 over 2 m omega squared x squared. And the omega is going to be the, which is something which I just use the fact that the K, the rigidity, can be written as the frequency of the oscillation and the mass of the oscillator. And you see that the omega is going to be we can talk about that as the frequency of the oscillation. And in this picture, you see that this oscillation, a different harmonic oscillator, and the frequencies, you see that it shows a different, I should say, amplitudes, and which is in that going to be that picture. However, before we finish this part, I'm just going to say that in the quantum physics, we just use the concepts of the energy as essentially something that we talk about the kinetic energy and the potential energy, but the only thing is that we look at the momentum and the displacement as an operator, and that's why I showed that this hat sign on top of those, I should say, parameters in the physics. By looking into that, it's going to be a little more advanced. I'm not going to go through this because in that sense, we have to also introduce two operators, which they call that creation operators, I dagger, and annihilation operators, A, which in a sense, it essentially creates more states with the same energy. I'm not going to talk into that, but I'm just going to write the final result that based on these concepts, we can just write, I should say, the total energy of the quantum physics of the quantum oscillator as this E sub n equals n plus 1 over 2 h bar omega. The omega is essentially, it's the same as a frequency as I talked about, and h bar is a Planck constant divided by 2 pi, and also we see that the n, look at that, n can be anything. N can be 0, n can be plus 1, n can be plus 2, and it goes all the way to the n. You see that if we just put n equal to 0, we get E0, which is going to be 1 over 2 h bar omega, and that's the thing that they call that the zero energy, which is a concept which we do not have a similar thing in the classical physics, because we define the energy of this oscillator as long as it is moving. But in the quantum physics, we see that we can discuss about that even though that there is no motion. And as a very last part, which I'm just going to talk about, and I'm going to talk about and just see the relevance of this energy quantization is the concepts of the lasers. You see that on this picture, a lasers as a coherent source of the light. And I'm just going to talk how that thing is created. But before we do that, I'm just going to define, before I just go to show how these, I should say, diagrams, what kind of information they carry, I'm just going to talk about what do we mean by the quantization energy concepts in, I should say, in the applications for the lasers. Look at these two distinct and discrete states which I have just thrown here. I'm just going to call this one G in a ket state as a Dirac notation, which it shows, I should say, the ground state of the atom. And the other one, I'm just going to show that with the E, which it shows that it's going to be the excited state of the atom. That's the concepts that in the quantum optics, they define this as a two-level state atoms. And now imagine that I have an atom, which is at the ground state, and I just excite that atom by sending, I should say, a pulse, or let's say, for example, a radiation, with the energy h nu, with the frequency h nu, which is going to be greater than the ground state energy of this atom, which it induces essentially this atom to go to the excited state, the first and the only excited states, and spend some time there. However, because this excited state is unstable, the same, I should say, the same atom over here, we see that it's gonna decay back, essentially, coming back to the same level which it just used to before, with a fraction of the time. And by doing that, we see that there is gonna be another radiation, which is gonna be h nu prime. Normally, nu and nu prime, the frequency are gonna be, in ideal situations, are gonna be equal, but sometimes because of, I should say, the crystal, I should say, phonons, normally the nu naught is less than the nu of the initial photon, which is excited, and some of the energy is reduced due to heat. We are just going to use the same thing for the lasers. Imagine, please come to these diagrams here. You see that we have the same concepts. We have the ground state, we have the excited states, E1 and E2, an incoming photon and radiation comes to excite the atom, goes to the other state. As I said, this one decays back, comes back to the ground state by sending another photon. You see that we have now two photons. The first photon was the incident photon, and the second photon was the photon which is emitted from, I should say, the decay from the excited states to the ground state. And now we can see that these two different energy, it comes with the emission energy, which is, I should say, comes after the emission. And now imagine that if I have, for example, if I can trap these radiations. For example, I have the mirror. These photons comes here, they get reflected back, and they come back, I should say, to the same medium and excited back again, going to the same level. And that's the thing which we have used it here. Imagine that. We have two mirrors that when we excite the atom, these emitted radiations get reflected back to the mirror and comes back again to the same medium, and again they excited the medium back again to the upper states, and again they induce another radiation. And if again there is another mirror here, again many photons, they again come back, reflects back, and induces more excitations of my two-state atom and creates more energy. And you can just combine them together, and you see that they superimpose, and you have at the end, you get higher energy. And that's the reason with the energy concepts of the lasers, you can harness a tremendous amount of the energy with the lasers then. Okay, now I'm just reaching towards the end of my lectures, and I hope that I had so much fun working on this presentation to talk about the quantization. And thanks a million for your attention and for listening to my presentation. Thanks a lot.